Cool. So yeah, my name's Sam Arch. I'm visiting from Carnegie Mellon University. I'm a third-year PhD student, and I'm focusing on databases, specifically UDFs. And yeah, so today I'm going to be talking about this. Dear UDFs, I broke up with you, but now I'm ready to give you a second chance. Will you take me back? Sincerely, SQL. So there's been a troubled relationship spanning many decades between SQL and UDFs. And today I'm interested in exploring this relationship and finally answering this question: are SQL and UDFs finally ready to be together? So for an overview of this talk, I'm going to give some background on UDFs, then go into existing UDF optimization techniques in the literature to make queries with UDFs run faster, and then finally talk about our new optimizer for UDFs that's been accepted for publication to VLDB 2025. Cool. So user-defined functions, or UDFs for short, are procedural functions written in some non-SQL programming language, like Python or PL/SQL. Today I'm going to be talking about PL/SQL, but most of what I'm describing applies to any of these other programming languages. And these UDFs are callable from SQL queries in the same way that you would call a built-in function, like substring or something like that. And when you call these functions from your SQL query, they're invoked natively inside of the database system. So as an example for PL/SQL, imagine we want to write a query like this, where we want to show all the customers and whether they're a VIP. Well, whether a customer is a VIP is specific business logic, so there's not going to be a built-in function for that. So you need to create a UDF in order to do that. So we're going to create a UDF isVIP that takes in a specific customer key and tells us whether they're a VIP or not. So to create this UDF, we're going to use this create function command. The name of our UDF is VIP. Any input parameters, in this case just the customer key, and it returns a Boolean whether they're a VIP or not. To do this, we have two variables. One variable is total, which is a decimal, the total amount of money spent on orders by this customer, and a Boolean VIP, whether they're a VIP or not. So in order to, the logic for this UDF is that we compute the total amount of money spent on orders using this select statement inside of the UDF, which is just going to accumulate, sum up this column, O total price, for every single order made by this customer. And then we save that in a variable total. And then if the customer has spent more than $1 million, then we set VIP to true, else VIP is false, and then we return. So by creating this UDF, what we get is code reuse, because we can invoke this UDF from any of our SQL queries. It's readable, because we're decoupling the UDF logic from the SQL query rather than putting the whole thing in SQL. And it's modular. If we want to create complex SQL queries, we can break it down into small reusable UDFs. So today I'm talking about PL/SQL, but why do we care about PL/SQL? That's a strange programming language. In fact, most people here probably haven't heard of it. Well, it turns out that it's actually one of the most popular programming languages for UDFs, far more popular than any other programming language for UDFs, because these systems, 3 of the 5 major most used database systems, Postgres, Microsoft, and Oracle, all support some dialect of PL/SQL. And if you don't believe me, there's this quote from 2017 from Microsoft, which says, there are on the order of tens of millions of T-SQL UDFs, T-SQL being Microsoft's dialect of PL/SQL, in use today in the Microsoft Azure SQL database service with billions of daily invocations. So essentially, there are billions of queries every single day calling PL/SQL UDFs. So making these UDFs run fast is very, very important. But the title of my talk is about this troubled relationship between SQL and UDFs. Everything I've talked about so far makes it sound like UDFs are great. What's wrong with UDFs? Well, the answer is R-bar execution. So what is R-bar? What does R-bar stand for? It stands for row by agonizing row. And this explains why there's such a troubled relationship between SQL and UDFs, because queries that call UDFs are so slow. So to explain R-bar, we go back to this motivating example of our query that calls our UDF. And what it's going to do is it's going to invoke this UDF for every single row of the customer table, just like you would invoke a built-in function. And then, let's say we have customer key 1. The database system is going to execute all the lines of code in the UDF line by line with customer key 1. And when it hits this line, if you don't have an index on your orders table, when it evaluates this select statement, it's going to scan the entire orders table to accumulate the total amount of money spent just for customer 1. So just for this one UDF invocation, we've scanned the entire orders table. So what this means is if we're calling this UDF for every single row of the customer table, and every time we call it, we scan the orders table, the complexity of this query is in the number of customers times by the number of orders. So because of this, we end up with an extremely slow query. If we have a very small database which only has 1 million customers and 1 million orders, that's 1 trillion operations to answer this query, and it's not going to execute in any reasonable amount of time. So this is what R bar is about, because row by agonizing row, we're forced to call the UDF. And as a result, UDFs have gotten a very bad reputation in the database community. In fact, there's this very famous blog post from 2006 basically saying that UDFs are evil and no one should ever use them. But this all changed now that in the research community, people have come up with techniques to optimize these UDFs more effectively. And in particular, the biggest advance in UDF optimization came from this paper out of Microsoft on UDF inlining, which was popularized with this paper called Freud out of Microsoft's Gray Systems Lab. So Freud stands for a framework for the optimization of imperative programs in a relational database. And essentially, it's about optimizing these queries that invoke UDFs. So Freud and UDF inlining is such a big deal because in their paper, they demonstrated that they can make real-world customer queries with these PL SQL UDFs up to 1,000 times faster. And in fact, it's such a big deal that it actually was implemented as a feature that was shipped in SQL Server 2019 called scalar UDF inlining. So what this means is if you write a SQL query that invokes a UDF in SQL Server, out of the box, it's applying Freud and this UDF inlining technique automatically for you. So how does Freud work? It sounds like magic. Well, the key insight is as follows. At the top, we have a SQL query that invokes this UDF row by agonizing row. And the way that it's being invoked in a row-by-row fashion is very similar to the way that subqueries are invoked in SQL statements. So conceptually, the way that a subquery gets executed is for every single row of the outer table, you're going to reevaluate the subquery. So essentially, the way logically you think about a UDF in a query and a subquery in a query is the same. But the difference, of course, is that subqueries have existed for a very long time, and there are decades of research on how to optimize subqueries. And in fact, most database systems, they can unnest these subqueries and eliminate the subquery entirely, replacing it with joins. So even though you've logically written a query with a subquery, it's not reevaluating the subquery over and over again. It's very efficiently evaluating it with joins. So the key idea of Freud, or UDF inlining in general, is if you can somehow translate this UDF into an equivalent SQL subquery, then the database system will know how to optimize it because it's just pure SQL, and you can get really good performance. So the way that UDF inlining works is done in 3 key steps. The first step, you translate each of the statements or lines of code in the UDF to SQL tables. Second, you chain the tables together with lateral joins. And lastly, you replace the UDF call, this is the inlining step, with the translated SQL expression as a SQL subquery. So because you're swapping this function call with this translated SQL code, that's where the inlining name comes from. So using our isVIP example, we want to translate each of these statements to tables. So let's take the first statement, total equals the result of some query. That's just going to be translated to selecting that query result as a column called total in this table T1 that we're creating. So what this is going to do is it's going to create a table which is 1 column containing the total column and 1 row containing the result of this SQL query. And this is equivalent to this original statement. But you can also do more complicated things. So for example, the if-else logic, that can be translated into a case-when statement. And then this case-when is just going to save the result as VIP, again in another table T2. So once we've translated all of these tables, all of these statements into SQL tables, we have a problem, which is that subsequent tables are actually referring to columns from the previous tables. So here, this case-when logic actually requires accessing the column from table T1. But in general, in SQL, you can't access other tables' columns. So the way that this can be fixed is by using this magic keyword called lateral. So when you add this lateral keyword between tables in SQL, it creates a lateral join between these tables. And in SQL, when you have a lateral join, later tables can refer to previous tables' columns in the lateral join. And conceptually, the way you can think about lateral joins executing is as a bunch of nested loops. So for every single row from this T1 table, we're going to compute T2. And if you have a bunch of lateral joins, it's like a bunch of nested loops. And because it's nested loops, it can refer to the columns from the outer loops. That's essentially how it works. So anyways, by doing this lateral join between all these tables, we can resolve all of these references, and you can see that in T2, we have the result that we want, which is whether the customer is a VIP or not. So all we need to do is select that VIP out from table T2, and then this whole expression here is equivalent to the original UDF. So the last step is that we just have to inline or replace the UDF call with this translated SQL expression as a subquery. And once we've done that, what we're left with is a pure SQL query without any UDF calls, because inlining essentially removes all of those UDF calls by translating them to SQL. So this is why Freud is able to get such huge speedups, up to 1,000x, because you've gone from a UDF call, which is an opaque function that the database system can't optimize effectively, into a pure SQL query that has decades of research behind it in terms of how to optimize it. But unfortunately, this SQL query is actually really complicated. And even though you've translated the problem, so now it's all in SQL, real database systems struggle to optimize queries that look like this because it has a complicated subquery with lateral joins and so forth. And in fact, when this subquery can't get unnested or removed by the database system, it's essentially just reevaluating the subquery row by row in the same way it was reevaluating the UDF row by row. So really, if the database system can't optimize such a complex query, it's still R-bar execution, even though it's now in SQL instead of doing the UDF call. So the reason why the database system can't actually optimize this comes down to a key optimization called subquery unnesting, which is really just how the database system removes subqueries. So imagine we have a simple subquery like this, where we're selecting some subquery for every row from this orders table. Well, the subquery is just getting the customer who made the specific order. So again, the naive way that this would get evaluated is you keep rescanning the customer table for every order. But pretty much every single database system will rewrite this to do a join between the customer and orders table. So instead of it being customers times orders, it's going to be customers plus orders if you use a hash join or something like that. But the challenge is that if you have an extremely complicated subquery like this, the database system can't unnest it, and you're left with R-bar execution. And what we find is that when we run this benchmark from Microsoft called the Microsoft Proc Bench, which is like TPC-DS rewritten to use UDFs, what we find is that SQL Server can only unnest 4 out of 15 of the queries when you use Freud or when you inline UDFs. So what that means is for the vast majority of queries, real-world queries, inlining is not really solving the problem. But there is a way to solve this problem, because because there is this paper from 2015 from Germany, from TU Munich, called Unnesting Arbitrary Queries. And what this paper allows you to do is systematically eliminate any subquery, no matter how complicated it is, even if it contains lateral joins. But how many systems actually implement this algorithm? Well, DuckDB implements it, and it can unnest arbitrary queries. But unfortunately, DuckDB didn't support lateral joins. So if you inline a query, if you inline a UDF, it has all these lateral joins. So even though it can unnest arbitrary queries, if it doesn't support lateral joins, you can't execute inline UDFs. But I needed this for my research, so I basically had no choice, and I spent a semester with 2 master's students implementing lateral joins in DuckDB. So we submitted a pull request, which has since been merged as of version 0.9 of DuckDB. And here's the QR code for the pull request if you want to check it out. So after this, basically, if you inline UDFs and then you run them on DuckDB, because it can be unnested, because it implements this algorithm where it can unnest arbitrary queries, now for all 15 queries in this benchmark, you can get really good performance because the database system unnests it and uses joins. But unfortunately, if you're not running on a system like DuckDB, which is pretty much everyone, then you're still left with slow, painful R-bar execution, and it sucks. So this is why there's this troubled relationship between SQL and UDFs, because UDFs are still slow. And this is not the only troubled relationship. While all of this is happening, I'm doing long distance with my girlfriend back in Australia, and I'm staying up, and I'm calling her at night, going across time zones. And then my advisor DMs me on Slack, and he says, "Listen, Sam, if you're serious about databases, you need to break up with your girlfriend. This long distance thing is taking up way too much of your time." Now, normally I would question something like this, but he is one of the best database researchers in the world, so who am I to argue? But at the same time, I'm not going to fly all the way to Australia just to break up with my girlfriend and then fly back. So I just sent her this breakup text, long distance isn't working out so great for us, we should see other people. And that's actually how I got the idea for the title of my next paper, Dear User-Defined Functions, Inlining Isn't Working Out So Great for Us, Let's Try Batching to Make Our Relationship Work, Sincerely SQL. And this was published in CIDR at the beginning of the year. Now, batching doesn't really work either. The summary of this paper is essentially just inlining doesn't work. Really, nothing works, and it's a very dire situation to be in. So that led me to this question of why is it that queries with UDFs with inlining are so slow? And fundamentally, the answer is that we're inlining the whole UDF. You have this UDF, you translate all of it into SQL, and you're going to get this very complicated subquery with lateral joins, and then the database system is stuck executing it bar. But really, do we really need to inline the whole UDF? If you look at this UDF, what do we really care about inlining? Just this select statement at the end of the day, not the rest of it. Or in other words, is there a way that we can outline or hide everything in the UDF that the query optimizer doesn't need to know about? So what we did is we actually came up with a technique, UDF outlining, which does exactly what I just described and makes queries with UDFs way, way faster than inlining. And this is the basis of our 2025 VLDB paper, The Key to Effective UDF Optimization Before Inlining, First Perform Outlining from Carnegie Mellon University. So basically what we did is we implemented this UDF outlining technique as well as a bunch of different complementary optimizations in an optimizing compiler that we call Prism. And Prism is a 5-letter acronym just like Freud, but the reason why we call it that is because it's like a prism of light. What it does is it takes in a UDF, which mixes pieces that you care about inlining and don't care about inlining, and it breaks it up into its constituent pieces. So maybe piece 0 you want to inline and expose to the query optimizer, and piece 1 you don't care, and you leave it as a UDF call that's either compiled or interpreted by the database system as a UDF call. And the reason it's called Prism is because it's a 5-letter acronym for the 5 different optimizations that we implement in this compiler: predicate hoisting, region-based UDF outlining, instruction elimination, subquery elision, and query motion. The last one is a bit sketchy, but it works. So today I'm just going to be talking about these 3 optimizations in the middle. If you're interested in the others, then you can read the paper, which will be public soon. So the first optimization, which is the most important, is region-based UDF outlining. So the idea is we want to get rid of or outline the code that's irrelevant to the query optimizer. So what we can do is we can observe that this block of code, ignoring the select, is the block of code that we really don't care about exposing to the optimizer. So what we want to do is we want to extract it out into its own function, or sort of leave it as a UDF call, so it's hidden from the query optimizer. And the reason we can do this is because this is what's called a region in compiler's terminology. So essentially, the only way to enter into this block of code is by executing the previous line of code and hitting the if. And similarly, there's only one way to exit this block of code, which is by leaving it from the return statement at the end. So this is single entry, single exit, and as a result, it's a region in compiler's terminology. And what that means is that as long as we think about what inputs we need to provide into it and what outputs we can get from the end, we can essentially extract it into its own function, replace this block of code with a UDF, with a function call, and then get an equivalent result. So we do exactly that. This takes as input total, and it returns a VIP variable. So we can replace it with a function call, f total, as long as f is doing the equivalent logic to this block of code. So what we do is we create a function, f, takes in total, does the same if-else logic, and returns this VIP variable. And then coming back to here, because this function f does the same exact thing as this region, you can get rid of the region now that it's been outlined. And what we're left with is a significantly simpler UDF than what we had before, because the complexity has been extracted out into a UDF call rather than being inlined to the query optimizer. But we're not done. Suppose we were to inline this as is. Well, remember that with inlining, we translate each of the statements into SQL tables and stick lateral joins between them. But we want to get rid of all the lateral joins. So really, to get rid of those lateral joins, we want to get rid of the statements in the UDF as much as possible. So in this case, we're assigning the result of this select to total, and then immediately passing it in to this function called f. But really, you can see that this variable total is pretty much redundant. So what we can do is we can eliminate that instruction by just forwarding the result of the select directly into the function call. And by doing this optimization, instruction elimination, we're basically left with a single line of code. So if you were to inline this, you wouldn't get any lateral joins. And then the last optimization I'm going to talk about is called subquery elision. So normally the way that it works with inlining is you have to translate the UDF into a subquery. But actually, because we're just returning a single value, we can just directly inject the return value of the UDF in place of the UDF call. And by doing that, we're essentially left with a SQL query, which is very, very simple and has 0 lateral joins. And as a result, it's significantly easier to optimize compared to the inlined UDF, where you inline the whole thing, and this gets executed RBAR, whereas with Prism, you get a much simpler query, which is much easier to optimize. So going into the experiments, we implemented this Prism approach in DuckDB and also SQL Server, and we ran this Microsoft Proc bench at a 10 gigabyte scale factor. And like I was talking about before, it's essentially just TPC-DS rewritten to use these real-world UDFs. We ran on a Xeon 20-core CPU with hyperthreading, 192 gigs of DDR4 RAM, 960 gig NVMe SSD drive, and we built column store indexes on SQL Server. So SQL Server is a row store, but we created column store indexes, and that essentially allows it to push scans, predicates, and expressions on columnar storage instead of row storage. And we did 2 cold runs in order to load the pages into the buffer pool, and then 5 hot runs, and took an average of the 5 hot runs. But the result of the hot runs was very stable. So the first experiment is essentially testing the unnesting. So if you recall before, only 4 out of 15 of the queries could be unnested when you inline the entire thing because it's so complicated. But with Prism, we find that 12 out of 15 of the queries can be unnested because, again, we're producing a much simpler query where you're only inlining the pieces that are actually helpful for query optimization instead of the whole thing. So for these 8 out of 15 queries, which is more than half of the benchmark, it's going to efficiently execute those queries with joins instead of RBAR, and you're going to get much better performance. And like I was explaining before, because DuckDB can unnest arbitrary queries because of this fancy algorithm from Germany, it's basically going to do 15 out of 15, regardless of how complex or simple the generated query is. So in order to understand the performance, we split it into average speedup and maximum speedup. So there's some queries that are just abnormally fast using our approach, so we exclude them from the average. So the average is excluding outliers. So for SQL Server, we find that there's a 298.7x speedup using our approach. And again, this is because of unnesting. Because for more than half of the queries, 8 out of 15, they can be now unnested with Prism because we're producing simpler queries compared to inlining the whole thing. And that's joins instead of RBAR, and that's why it's so much faster. And similarly, you can get a maximum speedup of 3000x because you basically think, OK, in my query, what's the bottleneck? If the bottleneck is the UDF, and then you replace that RBAR call with joins, because you can unnest that inline UDF, then basically you're going to get like a huge arbitrary speedup as you increase the size of the data. So again, using Prism gets you this huge win of inlining the entire UDF. Now for DuckDB, we actually didn't expect any performance improvement. And the reason why is because, like I said, it can unnest anything no matter what you do. Why does it matter if you produce a simpler query? But it turns out that we still got a 1.29x improvement. And the reason why is because inlining produces lots of lateral joins, which need to be executed by the database system. Whereas by hiding the complexity in the UDF call, you have fewer lateral joins, which are faster to execute. And lastly, for the maximum speedup, there's this one query which is over 2,000 times faster to execute with Prism versus inlining the entire UDF. And the reason why is because even though DuckDB can unnest any arbitrary query, when you give it this very complicated query, it picks a very bad query plan. Meanwhile, with us, with Prism, because we're producing a simple query, the database system can it's much easier for the database system to find a faster query plan, and it ends up being super, super fast. And the difference in query plan is that the first query plan is doing a hash table. It's probing a hash table with 250 billion input tuples because there's a cross product in the plan. Whereas with our plan, it just efficiently uses a hash join and then finishes in less than 2 seconds. So to answer the question, are SQL and UDFs finally ready to be together? Well, I say yes. If you use the right techniques, then UDFs can be executed efficiently by the database system, and then you're going to get really good performance as well as all those benefits of UDFs like code reuse, modularity, and readability. So this begs the question, if SQL and UDFs can repair their relationship, maybe I can repair the relationship with my ex. So I sent her this text, I broke up with you, but now I'm ready to give you a second chance. Will you take me back? But unfortunately, my text message actually didn't go through. And the reason why is because she blocked me on every single social media platform. So to conclude, UDFs are awesome, but they're very hard to optimize. And as I've gone through, all of this space of UDF and subquery optimization is very, very tricky and possibly one of the most complicated parts of the database system. But what we find with our work is that you need this inlining and outlining in order to get the best possible performance. It's not enough to just inline the entire UDF. You only want to inline the pieces that are actually helpful for query optimization. And for my next project, I'm interested in Python UDFs, specifically because everyone is using AI, ML, data science, and making these Python UDFs fast is really the goal of mine for my next project. Thank you.